The students try to please understand. Materials are, yesterday I have shown you some demonstration about the behavior of wire under increasing load. Behavior of wire under increasing load. Right. Now, following which, just want to remind you one more aspect. That is, the same stress strain graph gives you different information. I told you very clearly in my last class. Now you can see here in this part, you're plotting stress versus strain graph, and you see you have a straight line region, and this is the region where Hooke's law is valid. And the plastic region between E and C here. E and C, yesterday I told you, plastic region between E and C. This zone represents to classify the material to brittle or ductile. For example, you take glass. For glass, if you draw this graph, for glass, if you plot stress strain graph, the gaps will be narrow. The region between E and C will be narrow. So that is the reason why they will break immediately after elastic limit is crossed. In our graph, I told you this is proportionality limit, this is elastic limit. After that, the gap is very small. The region is narrow. Such materials will come under brittle material. On the other hand, you see for ductile material, like you will see copper wires for current purposes. You will have electrical wires. So thin leads you will see. To prepare such a thin lead, you need to mold the material like that, thin, very thin. So the material of this wire has a good range between the elastic limit and the fracture point. So this gap is wider, you can see. So they will have a good plastic range. That is the reason why these materials are called as a ductile material. You can mold them into different shapes. That is the reason why gold ornaments, silver ornaments, they can make it in different shapes because of this feature only. And there are another nature, like some materials called elastomers. The first identity of elastomers is that the stress versus strain graph is not a straight line, bit curved. And the strain produced is much larger than the stress applied. You can see that. See, the increment along X is more than the increment along Y. This material do not have a plastic range, which means you don't see such a range in this material. And the breaking point of the material almost C lies close to E. In other words, E and C, two such things do not happen. Once you reach E, almost you have reached the breaking point. The problem with these materials is they do not follow straight line behavior in stress strain graph. It's bit curved. And so there is no proportionality limit in this graph because there is no straight line behavior. So straight away they will reach this point, which is E or C. There is no plastic range. Example, rubber. Right. There is another property, elastic hysteresis. Now you see, for a wire, what I am doing is, I am following a stress strain graph. Say the graph followed a path till here. Now I am removing the load gradually. And finally, I made the load to 0. What the part that I assume in the forward direction is missing in the reverse direction. which means there is some delay. I repeat, there is some delay or lag. There is a lag in stress strain graph. You can see that. When deforming force is applied on a body, strain does not change simultaneously with stress. Rather, it lags behind stress. So, this lagging of strain behind the stress is defined as elastic hysteresis. Hysteresis is referred to lag. Okay. So that is the reason why the values of strain for same stress are different while increasing the load and while decreasing the load. Say for example, when I put, say for example, 200 grams, that time strain while loading, that time while strain while unloading is different. It takes some time to settle down actually, right? So the area of stress strain curve is called a hysteresis loop. Hysteresis loop. And this is numerically equal to work done in loading the material and unloading it. I repeat, area gives work done in loading and unloading the material. This is a very important theory area. So I have discussed that here right now. Right. This is a very famous paragraph. N number of times we got this. I'll discuss that right now. In the figure shown, A and B are two short steel rods, each of cross-sectional areas 5 centimeters square. The lower ends of A and B are welded. This is also an important point. Lower ends of A and B are welded. To a fixed plate CD, you can imagine like this, like a ground. Right. The upper end of A is welded to the L shape. This is also an important data for me. In fact, A is welded. So A is welded, right? Now, but it can slide freely on B. A horizontal pull force of 200 newtons is exerted at G as shown. Neglect the weight of EFG. Now, what happens? Please try to understand what is happening over here. See, I am drawing the free body diagram of the frame, L-shaped frame. In the portion of A, you will find some force like this. Of course, you are applying some force, 1200. And not only that, at this point, A will exert some normal reaction force also because it's about to be turning effect. So this is the actual longitudinal, okay, right. So this is the picture what you need to know. Just please give me a clarity whether you understood this or not. I'm repeating the question again. Everyone try to please go through the question once. Okay. So at E, at F, at G, 1 minute. And they should have some weight also, no? There is one more force here. N1, N2. That's it. So some of the upward forces balances, some of the downward forces should balance for the equilibrium. Now, everything lies here. Now, only information given to me is this force. I can confidently say that this force is F. F is obviously 1200 Newton. Now we will draw the free body diagrams of A. This is A. The free body diagram of A is the free body diagram of A is, see, action, reaction. Friction, actually. This force is friction. Next, so on B, you have N2, N3, Mg. Here also there is another N4. That's all. Now, entire question depends on your capability to understand the free body diagram. Mark out the correct statement. Shear stress in A is 0. Wrong. In fact, A will experience shear stress because there is a tangential force. Shear stress in B is 0. Correct, because this portion is not welded. Shear stress, wrong. In B, 0. In A, non-zero. Wrong. So, in fact, shear stress in A is simply F by A. Right. About at this point, we will take up the rotational equilibrium. Yes, you can take it. How I will explain. Net torque about E is equal to 0. N2 times 4 is equal to 1200 times 3. So clearly N2 is equal to 900 Newton. Don't forget, this is the same as N1. Why? Because on the frame, net upward force is 0. Neglect the weight of EFG. That is also an important term, which means N1 must be N2 for this. Right? There is a part I have done. Longitudinal stress in A. What is longitudinal stress in A? Obviously, longitudinal stress in A is nothing but N1 by A. N1, right. Longitudinal stress in A is equal to N1 by cross-sectional area. I know what is N1, which is 900. Area of cross-section, which is 5 centimeters square, which can be written as 5 into 10 power minus 4. Yeah, right. 18 into 10 power 5 Newton per meter square. That's the longitudinal, right. Or you can write this in another way. It is like 180 Newton per centimeter square also you can write, no issues. So one is correct, two is wrong. It's not compressive in case of A. It is elongative because you can see space is pulled up. Longitudinal stress in B, it is actually compressive in nature. Same magnitude, compressive in nature. Magnitude is same only. So longitudinal stress in B is N2 by A, which you can write it as, again the same, 900 by 5 into 10 power minus 4, which is 180 Newton per centimeter square. I am telling you, this is a very, very, very good model. Should not miss this. Someone please confirm whether you understood this or not. Rohit, just see that. Rohit, are you sure students followed that?
Yes, sir.
Yes. Thank you. Right. Next model. Some models like this we need to do. I have covered all these questions. Now, one more. This is one more point. Please see this. You can imagine a cylindrical portion. In this cylindrical portion, you can see at this point some F force is acting. At this point, some F force is acting. Right. Now they imagined that there is a portion AB, which is slanting. The plane is slanting. Make some angle theta. Right. So what they want is the shear stress here. Please try to understand at this point. Resolve this into components. If this is a theta, this is a theta. So this is F sin theta. This is F cos theta. So, and one more important point, area. See, this is a small area, don't forget that. What is tangential force? Tangential component of force by area, tangential area. See, if this is A area, this area becomes A by sin theta. Okay? This area becomes A by sin theta. So tangential force is F cos theta. Tangential area is A by sin theta because the force is in this direction. F cos theta. So this is the shearing stress. What about longitudinal stress? Longitudinal stress is normal force by tangential area. F sin theta by A by sin theta. F sin square theta by A. This is a very famous model, an important model. I want confirmation from students' side. Have you understood this? Yes or no? Just confirmation. Rohit, confirm whether students followed or not. Rohit,
Yes, sir. Yes, sir.
right. All this I have covered yesterday in the class. Yeah. You imagine a situation like this, where the rod experience different forces at different points. You can see The point of application of the forces, entire thing is thin rod. The thin rod, entire single piece thin rod. I applied 50 kilonewton force here, 20 kilonewton force here, 10 kilonewton force here, 60 kilonewton force here. One thing that I have started yesterday while I was doing numericals, I told you clearly what was my very first step. My very first step is net force. 70 newtons, 70 newtons. Net zero. Not element wise you take. First, we'll call this 1, we'll call this 2, we'll call this 3. Now, let us take 1. No, yesterday's concept don't forget. If you are exerting yesterday's concept, a force F on a rod of length L, cross-sectional area A, Young's modulus Y, the elongation is F into L by AY. I am using this concept now. I am taking the first part where 60 Newton, this portion must be in equilibrium, 60 Newtons. Yes, the elongation contribution here, follow this formula. Now you take the second part. Now action. So additionally 10 Newtons is acting on this portion. Which way? This portion, second one. This 60 counter is 60 plus 10, 70. For this to be in equilibrium, 70 the other side. Same formula again, E2. I got it. Next, the third part. This is the third part. Third part, second part, first part. Yeah, 1 minute. For second, right side is 70. So third left side must be same actually, but 70 minus 20. The net is 50. You are exerting 50. So therefore, same formula. So portion 1 elongation, portion 2 elongation, portion 3 elongation. All elongations put together, you got around 1.3 micrometer. A very, very, very important model. I want a confirmation from your side. Say yes or no for this. Have you understood this or not?
Yes, sir. Yes, sir.
Right. 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 Already we have done this model. Right. 1 minute. That's the answer. This is a smooth flow. Right. You want the total elongation. See, for this technique is simple. Yesterday, do you remember I have given you one relation? Yesterday, I have given you one relation. On a smooth floor, if you are applying force F, length L, cross-sectional area A, Young's modulus Y. In this case, the elongation is, yesterday we have derived this. Try to recall. Now, in this case, net force is F. So, in this case, what I have done is, if I treat this problem same as a problem like this, yeah, in the reference frame of the rod, I can see that F by 2, F by 2. In this case, the elongation is, Aryan, see, please try to remember. In this case, elongation is F into L by AY. In this case, the elongation is F to AY. Same concept we got. Similarly, now you see here, total net force is again 3F. I mean, add all the forces. Remember, not net. What I have done here, F by 2 plus F by 2 is F. F plus 2F is 3F. Remember, this technique is applicable only under one condition. What is that? The forces must be applied only along the ends. Now, I'll take up this entire situation as 3F by 2, 3F by 2. Length L, cross-sectional area A, X modulus Y. Yes, E is simply 3F by 2 times L by AY. This is 3FL by 2AY. Are same answer. Short method for doing this. Shortest method to solve this question. One step. Remember, you are allowed to use this only under one condition. Only when the forces are applied left and right. So, in general, suppose if you are having a situation like this, both are elongative forces. If it is F1 and this is F2, now I will write the elongation as F1 plus F2 by 2 times L by AY. That's how I'll write. Next. Rohit, confirmation.
Yes, sir. Yes.
Right. Now, series and parallel combination of rods. See, when you are stretching a rod, like F force, length L, area of cross section A, Y. We already know this is stress. Young's modulus times strain. This is stress, and this part is strain. In this case, F is YAL by YA by L times E. Hello, Roy. Now you can see this situation can be replaced like a spring experiencing F force. In that case, you will write force is force constant, spring constant times elongation. So here the K term is like YA by L. So it is like comparing a rod to a spring. Now, two rods are connected in series. What is common? Tension is same in both the rods. In that case, it is as same as two springs connected like this. F is K1 E1 same as K2 E2. So E is E1 plus E2. E1 plus E2. E1 is F by K1 plus F by K2. Same step I have written here. F E is FL by Y1A plus FL2 by Y2A elongation. But this formula is a true same area of cross section, same A. What if area of cross sections are different? You will write obviously A1, A2 terms. Please confirm me. Have you understood the series combination of two rods? Yes or no? Anyone in the class?
Yes,
Rakesh?
sir.
Right, Rohit, sorry. Now
Yes, sir.
this is a parallel combination. This is a parallel combination of two rods. In parallel combination, stress or tension is different. L1 is equal to L2. Elongation is the same in this combination, parallel combination. So in that case, force applied balanced by tensions T1 plus T2. And you already know T is Y A E by L. Stress is Young's modulus times strain. I have simply used that relation Y1 A1 by LE plus Y2 A2 by LE. So overall elongation is expressed like this. That is simple application, right? This I have already given yesterday. 1 minute, let me check anything else missing. Theory point of view. I have done all. Strain energy also I have done yesterday only. Right, done all. Right, I need to close elasticity theory at least today. Already bulk modulus I have introduced. Bulk modulus means, can see, bulk modulus is stress by volume strain. Volume strain. So you can see here density of a compressed liquid. Normally density is given by mass by volume. Since mass won't change because it's the same, it's a fixed property. The differentiation part d rho by rho is minus dv by v. Now bulk modulus is delta p. Remember, no confusion between these two terms. No confusion between these two terms. So therefore delta v by v is, 1 minute, I'll give clarity because written by student last year. K is minus delta P by delta V by V, P by rho by rho. You can write it like this also. Right. So from this, delta rho by rho can be written as delta P by K. So obviously, what is delta rho? Final minus initial. Delta rho by rho means this one. This one. So I have used this. This is a very, very famous relation. A very, very famous relation. So you will have problems where you will simply directly substitute into this. Any doubt till this point, boys and girls? Any doubts? Right. And one more important point. This is a very famous question. Simple,
Hello, sir.
right?
Sir, please, can you repeat?
Rohit, yeah, what is the doubt in this?
Sir, can you please repeat it once?
Right. Now see, you have density is mass by volume. Now in this case, You do differentiation of this. That's it. Which I have substituted in our formula. This one I have substituted in bulk modulus formula. Thereby I got delta rho by rho is delta P. This is a different term. This is a different term. Don't get confused. Also, what is a delta rho? Final minus initial. Exactly what I have substituted there. Right? Next. Fractional change of radius. So your sphere here, already there is some pressure prior to adding this. The volume of the sphere is 4 by 3 pi r cube. For a small change, all this is a constant. So delta V by V, you just do differentiation. If you do differentiation, so if you want dV by V, so that gives you this relation. So delta R by R is 1 by 3 times delta V by V. Right. What is bulk modulus? In fact, the radius shrinks here. Delta R by R is 1/3 volume strain. That is nothing but delta P by K. Delta P is just because of the adding of this mg by A. So this is a very, very, very famous model. Tell me, have you understood this? Yes or no? Rohit.
Yes, sir. Yes, sir.
1 minute. The prior to this, you have an arrangement like this. In this case, this is some wire, mass negligible, carrying a load M. In this case, the tension in the wire is mg by A, cross-sectional area of the wire. Elongation is strain is stress by Young's modulus. We know this. Delta E by L. Delta E by L is equal to stress into Y. Delta E is F into L by A into Y. So that is the elongation. Here F is tension. So therefore, elongation is equal to AY. In this case, mass of wire is negligible. What if it is a rope of mass small m carrying a load m? Yesterday only I have derived elongation due to its own weight. Yesterday only I have derived this, which can be given as elongation due to own weight, mgl by 2ay. Now the question is, total elongation in this is two different things. One is elongation due to own weight. Next, elongation due to load. mgl by 2ay plus mgl by ay. So overall, you can write this as that's all. Both are famous relations. Even in mains also, you will get these questions where you will simply directly substitute the content and thereby you'll get the marks. Hope you have understood this. Now, a same model that you are expected to go with. What is that? Just erase this because you have the content. అది ఉన్న దగ్గర నుంచి నాకు డిస్టర్బెన్స్. Is a wire non-uniform wire. Elongation due to own weight of a non-uniform rope or wire. I think load of mass is given. I think you can neglect the mass of the wire. That is a different question actually, right? You can neglect the mass of the wire, but radius is changing linearly. You said that the radius changes from A to B. Remember how to write the function. It starts with A, B. Actually, the length at any instant is given as x. Total length is L. You form similar triangles then. This is Y. So two similar triangles you have. Y minus A by X is B minus A by L. So this is how you will write Y as a function of X equation. What is Y? The radius at a particular instant. So R minus A by X, radius taken along Y, depth taken along X. B minus C. R is equal to A plus so radius at a depth x. What is this? Radius at a point x below suspension. Right. See, try to please understand clearly this is a massless load. Clearly this is a massless load. Okay. So this is the radius of cross section at a depth x as mentioned. Right? No issues. Very comfortable till this point. Now my point is very clear here. Very important point. Tension at any cross section is the load of the wire itself, mg. Now, stress at the point is equal to mg by a, mg by pi r square, mg by pi times that is the stress at that point. Strain at that point is equal to stress by Young's modulus. That is the strain at that point, which can be given as dx. 1 minute. Elongation at that point by dx. Now dE is mg by pi y. Here, just allow me to write this as dx, where b is right. Now you need to write this part properly. See, you need to do the integration part properly. Because how I will do this question, I'll try to explain. Uh, 1 minute. Please allow me. Right. Now see, till this point, there is no doubt for you. Let us take integration as a criteria. That also you don't know, I know. You take a plus bx. dz is 0 plus bdx. Good. And now, after substituting all mg by pi y p 1 by z square dz, do the integration. So the total elongation is mg by pi y b times Actually, the integration is minus 1 by z. Yeah, please help me in writing the lower limit. When x is equal to 0, it is z is equal to a. When x is at z is nothing but the radius boss, right? It's b. When x is equal to L, z is equal to b. Therefore, you will get the relation as 1 by a minus 1 by b. That's the elongation part. So you can write this simply as mg by pi y. By the way, b is b minus a by L, and this is b minus a by ab. Cancel. Finally, the total elongation is mgl by pi y. It's a very famous relation. One should take care of this, a very famous relation. Yes, now I am shrinking this to single page. Please ask me, do you have any doubt at any point of this derivation? Please ask me right now. Rohit, confirmation.
Yes, sir.
Right, girls, any doubts? Right, right. See, you have a ring type structure. So what condition that I am discussing over here is rotation of a rigid ring. Rotation of a rigid ring. What I am seeing here, the situation is it's rotating about the axis, angular velocity of which being omega, and element which you are seeing over here will experience two forces. One is pseudo force. I'm taking lambda as mass per unit length of ring. Don't get confused. Lambda is mass by 2 pi r. Right. Now, already you know, in such situations, the angle between them will be 180. It's a situation like this. This is 180 minus d theta. Tension, pseudo force, lambda r omega square. You know, the resultant of these two will be 2t sine d theta by 2. If you are not convinced, t resultant square is t square plus t square plus 2t square cos 180 minus d theta. This will become 2t square minus 2t square sin d theta. 2t square times 1 minus sin d theta. This 1 minus cos d theta, sorry. That can be written as 2 sin d theta by 2. So T resultant is 2t sin d theta by 2. Remember, every time you need to remember, even next week also I will use at surface tension. So 2t sin d theta by 2 is lambda r omega square. When angle is small, very small, Sin d theta by 2 tends to d theta by 2. So T is lambda, which is m by 2 pi r times r times omega square. Mass per unit length. Here, one more important point I forgot here. I am getting calls, that time what happens is that I'll get disturbed. One step will gone. So here also, while I'm substituting d theta is lambda r d theta times r omega square, right? So tension is lambda r square omega square. Lambda is mass by 2 pi r times r square omega square. That's the D, r omega square by 2 pi. A very, very, very important relation. And please confirm whether you understood this or not. This time I have given even elementary and basic steps also. Please confirm. Sometimes what will happen is they will introduce one more point that is called breaking stress. Now you can see here, already you have studied in wire, behavior of a wire under increasing load. There is a stress beyond which if you apply, the wire will break. Breaking stress is equal to tension at that point by cross-sectional area. Remember, breaking stress is a property of material. That is a property of material, not on the basis of the dimension. But breaking tension depends on the dimension. So if you are taking two steel wires, thin wire, thick wire, both will have the same breaking stress, but both will not have the same breaking tension. That should be considered. Suppose the breaking stress, breaking tension is related as sigma A. In this case, they are rotating, increasing the speed, but you have a limit. Your tension must be, this tension must be less than whatever you rotate. This should be less than sigma A. If it is even equal to, the wire will break due to the rotation. So omega maximum allowed is 2 pi sigma A by mr. That's the deal. Okay, it's a very, very good question. If you have any doubts on this, please ask me once. Rotation of a rigid ring concept. Almost maximum theory I have covered. Right. Okay, just Rohit, confirmation.
Yes, sir.
Right. Now see, this is a cooker problem. Yes. You are using a gas in a cylindrical container. So when there is gas, for example, what will happen is that the cross-sectional area wherever you are seeing there, when see, as the gas pressure increases, a radial stretching take place, right? For example, if I'm seeing it from the top, it will try to exert forces on the wall so that there is a tension like this. For example, you have a situation like this. Suppose I'm filling water. I'm filling water. At this point, I know the pressure is a rho g h. Okay. See, the a putty जो है, this putty, this is of width dh, perimeter 2 pi r. So therefore, so you take a small element over here. 2t sine d theta by 2 is, this is the force, rho gh pressure into the element's area. How I will find the element's area? dh is the width, r d theta is the length of the arc. Arc times width is area. Area into pressure is force. So 2t sine d theta by 2 is this. So tension is rho g h minus small h times r dh. Now therefore, with this I can say T by dh is rho g h minus small h into r. So where you will have that part maximum when small h is equal to 0. Where it is a minimum at the top. So therefore, here it is a minimum. The tension part is minimum here. At this cross section, it is maximum because I have the relation. Same it is with the liquid. Suppose if gas you can see gas will exert pressure on all the walls and curved part as well as the base part. Now let us see the curved part first. The curved part first. 1 minute. సరిగా రాయలే హ్యాండ్ రైటింగ్ బాగా. Can you imagine? That's the cylinder filled with gas. Now let us try to see what is happening at two different regions. And this is a patti. Now, same concept again, tension, tension. So pressure is there. Is equal to Here the pressure is P, and the arc length is RD theta, and the width is dr. So T is P into radius of the container into dr. Suppose if you cut here, if the thickness of the wall is some T, now the width is dr. So therefore, sigma is defined at that point as dr times the thickness of the wall. So therefore, sigma dr T is P into R into dr. Dr cancel. So therefore, the pressure allowed maximum is this part, sigma T by R. Remember, this is the allowed pressure up to which the walls will not, the curved surface will not tear up on curved surface. Similarly, you will face pressure here also, no? Like the way you pressure here, you will experience a pressure here also. So this portion will experience a pressure force P into pi r square. Whereas on sides, there will be some restoring. So the tension part there is P into pi r square. And this can be written as, in this case, sigma into 2 pi r t. Because 2 pi r width, they have given t. Ansu. This is P pi r square. Pi cancel, R cancel. So pressure is 2 sigma T by R. So remember, as you increase pressure, inside the cylinder, at this pressure, tearing off takes place at the base. At this pressure, tearing off takes place at the cross section, curved surface. So what is minimum ante? You should take this as the minimum. So if that pressure is reached, tearing takes place at the curved surface, gas will leak from the curved surface. And puncture padite first akkada padutundi. Base దగ్గర పడదు. Curved surface దగ్గర పడుతుంది. Right. So any doubts on this, please ask me. If you have any doubts on this, please ask me. Rohit.
Understand, sir.
Right. This is also one famous model, H.C. Verma question. Estimate the change in the density of water in ocean at a depth of 400 meters below the surface. The density of water at the surface is given as 1030 kg per meter cube, and the bulk modulus of the water is also given. As you know, as the depth increases, free surface, H depth, we know when the density is keep changing, you are not used to write the pressure formula as rho gh. I told you n number of times, dp by dh is rho g. dp is rho g dh. But this dp is bulk modulus definition minus b, dv by v is rho g dh. Just now I have derived minus dv by v can be written as d rho by rho, rho g dH. Right. That's all. You do the integration part, you'll get the condition. Remember, 100% you will get this question. 100% you'll get this question, which means you need to solve this question in two ways. ఎందుకైనా మంచిది, I will derive this. So now I have two relations. One is d rho by rho square is d rho by rho square is g by b times dh. That's the relation. Now we will do integration here. H is equal to 0. Surface density is rho naught at some depth h. Let that density be rho. You know the integration for this is minus 1 by rho naught, rho is g by b times h. So which is 1 by rho naught minus 1 by rho is g by b times h. So 1 by rho naught is 1 by rho naught minus g by bh is 1 by rho. So therefore, you can write rho as b rho naught by b minus rho naught gh. What will this indicate is, as you go deeper, as h increases, rho increases. That's all. Why? Denominator decreases, fraction increases. This is about the density. One more important point, pressure aspect. See, one thing is clear, B times d rho by rho is dP from the definition of bulk modulus. Do the integration part now. Do the integration part now. So B times log E, surface pressure is P naught, density rho naught. At some point pressure is P, there the density is rho, is equal to P minus P naught. Implies P minus P naught is B times log E. Just now I have derived rho by rho naught is B by B minus rho GH, which means one definition is B times log E B by B minus rho naught GH. See, sometimes what we can observe is when rho naught GH is much, much smaller than D, B by B minus rho naught GH can almost be written as D. Okay. So in that case, you can write P as P naught plus B times log E 1 plus rho naught GH by B. That's the D. But sometimes what will happen, I'll explain. Sometimes what will happen is log expansion. log 1 plus x expansion, when it is very, very small, you already know this logarithm expansion, log 1 plus x expansion, what terms you will get if you go with the log expansion? Log 1 plus x can be written as x minus x square by 2 plus x cube by 3 plus so on. But for x much, much, much lesser than 1, log 1 plus x is almost x. So in that occasion, this is P naught plus D times rho naught GH by B, which is nothing but P naught plus rho GH. This is the formula which you know already. Remember, the actual formula is this. But this is a modified version of the above one. Okay? So please try to understand the truth in this. Now, please tell me, you have any doubt in this? Boys and girls, do you have any doubt in this? Sir Rohit, just please check with students.
Yes, sir.
Yes, sir. Right. So we'll move on to the next question. A very famous question, actually. A very famous question. Very famous question. Hmm. Just go through this. Don't see the solution. Just go through this. If you see a bimetallic rod made of brass and copper, lengths given, see that, and you have applied a compressive force. Remember, they are not too different. They are welded across the border. They are welded across the border. Now the question is, L brass. Now, suppose, see how to check. You do the compressions differently using our elongation formula, same as F into L by cross sectional. Same formula you use. I have substituted the data. When I have substituted the data, compression is high in brass when compared to the copper, which means it should be in such a way that, in fact, it will bend, not linearly compress. In fact, it will bend like this. Why? This length is less than this length. So therefore, it will bend brass side when compared to copper. Okay, it's a very good question. You should not miss. Next question. One more. Some models are there that I need to discuss actually. One minute. This is also another repeated model. Please work on this. Everyone. Everyone in the class. Materials get deformed when force is applied. Some of them regain their status when the applied force is removed. They are termed as elastic. Some basic information. They have given you some basic information. Those of which not regaining are called plastic. Right. There may be delay in the regaining in some materials. దాన్ని ఆఫ్టర్ ఎఫెక్ట్ అంటారు. ఆఫ్టర్ ఎఫెక్ట్. దానికి ఎలాస్టిక్ ఫెటిగ్ అని కూడా పిలుస్తారు. The delay in regaining its original size and shape after removal of deforming force is called elastic fatigue. This is a temporary loss of elastic behavior. Right. మీరే చూడండి. Sometimes what will happen is they will regain the shape after some delay time. Stress strain graph of two materials A and B is shown in the following figure. If the intensity of A and B is EA and EB respectively, then the stress strain graph of two materials A and B is shown. Right. Yeah, you can try. What is this region? material B. Next. Here intensity కాదు, I think elasticity. The elasticity of intensity కాదు. Modulus of elasticity. Obviously, very clear. Slope of OT is greater than slope of OM. So Young's modulus of A is greater than Young's modulus of B. Second option is correct. Next. The strength of material of A and B is SA and SB respectively, while the longevity of, obviously I can say very clearly from this, longevity of A is greater than longevity of B. Very clear, because we know from the graph L, this is corresponding to LA and this is corresponding to LB. The length of LA is more than the length of LB. Right? LA greater than LB. Only one option is available. And not only that, this is SA and this is SB. Clearly, SA is also greater than SB from graph. Next. First two questions are easy. The time in which the two material regains their original status is TA and TB, related to TB is 2TA. Time to regain in B is more than time to regain in case of A. Yes. So elastic fatigue ఎవరికి ఎక్కువ ఉంది? B కి ఎక్కువ ఉంది. So B. Elastic fatigue is high in B than A. ఆన్సర్ కూడా క్వశ్చన్ లోనే ఇచ్చేసాడు బయట. They have given the answer in the question itself. Okay, but still it's up to you. Please tell me, have you understood this or not? Rohit, confirmation.
Yes, sir. Yes.
Clear?
Yes.
Right. I'll proceed for one more question while I change. All these are standard questions actually. Last three questions. Right. Now, three questions, 10 minutes. 8 minutes actually. Fatafat karna. See first question. Very clear. I can comment. Slope of OP is greater than slope of OR. Remember, lot of students do one mistake. This is correct when strain is along x-axis, stress is along y-axis. So Young's modulus of A is greater than Young's modulus of B. But you see the breaking stress. You can see the breaking stress. Material A can withstand greater stress. True, because the ultimate tensile stress is high for A when compared to B. Because graph. S A, S B. S A greater than S B. Please confirm. Any doubts in this? Rohit,
Yes, sir.
next. 12th question. Yes, please go through. Where they are equally spaced. Uh, try to please understand that they are equally spaced. Heavy block of mass 150 kg hangs with the help of three vertical wires of equal length, equal cross-sectional area. Yeah, shown in figure. Wire is attached to the midpoint, center of mass of the block. Y2 is 2y1. This is y1, y2, y3. Right. Only information is y2 is 2y1. Right. See, for block to remain horizontal, remember, for block to remain horizontal, so torque at 1 must be same as a torque at 2, which means tension at 1 must be same as a tension at 2. Elongations are also same, which means y1 A by L times elongation is y3 A E. Are yaar tension ante ya by L into E. Y A same, L same, elongation same, because torques same, elongations same. So therefore tensions same. Therefore Young's modulus same. One correct. So because 2 is 1 minute. Because 2 is available, I have answered 1. When 2 is correct, 3 is wrong. Next, one more important point is tension is elongations is same in all the three. Hold on. So if tension is a T here, tension is a T here, at this point, the Young's modulus of this is double that of this. For the same elongation, Young's modulus is double. So 2T. And this carries the load mg. So 40 is mg. So therefore T is mg by 4, 150 by 4. Okay, tension. So 2T is 150 by 2. So therefore, this is a 75 kg weight. Right. 75 G another word. Right, correct. 4 is correct. Boys and girls, any doubt? Remember, tension is proportional to Young's modulus here. Because E same, A same, L same. A same, L same, E same. So in that case, tension is proportional to Young's modulus. That is the criteria to solve this question. Boys and girls, any doubts? Rohit,
Yes, sir.
clear?
Yes, sir.
Right. And the last question. I think this might take some time. 17th question. I can do this question only tomorrow because it's a lengthy question actually. Basically, it's a lengthy question. So why? Because I'll clearly explain. You need to draw the free body diagram, break it into pieces. Only then you can write this properly. It can be done. We'll do it tomorrow. No issues. Good question. This question need to be done something like this. I'll show you. Like this. Piecewise, you need to work. Right. So I'll stop the class here. In study hour, complete the homework which I have given to you. I have recorded this class. I'll post this class in YouTube immediately after I get the recording part. Right.